In this video, we'll be looking at the second part of the particle physics booklet, focusing on stable and unstable nuclei. Now, when looking at nuclei in greater detail, we need to consider the forces involved. It isn't just the particles, the forces that affect them and interact between them. Now, we have listed here the four key forces, the four fundamental forces that act on things in our universe. Now, gravitational force is the easiest to understand to begin with because we experience it in everyday life. And it affects mass and has infinite range. So no matter how far away an object is, it is affected by your own mass and your own gravitational field. It just drops off in strength dramatically at an exponential rate. So this is why the further away from a planet you move, the less affected by its gravity you are, but you still have that attraction. And exactly the same applies for the electromagnetic force, except instead of mass, we're dealing with charge. So the charge effect of either attraction or repulsion will affect at an infinite range, but exponentially weaker as you move the two charges apart. Now these other two forces are new, and they are both much shorter range and critical for understanding the nature of atoms. Now the strong nuclear force is between nucleons. There will be more detail on what this actually means later on, but that is enough for now. Whereas the weak nuclear force affects all particles, so that includes things like electrons that are not affected by the strong nuclear force. Now, as far as range goes, they're both very short range, and the weak nuclear force is shortest, but has some extra quirks to it. But you don't really need to know that detail. It will not come up in the exam. But for completion's sake, we will add it in here. And to maintain consistency, we'll put both of these in meters, but also introduce another measurement. So 10 to the minus 17 meters is technically the value for the weak nuclear force, whereas the strong nuclear force acts in 10 to the minus 15 meters, minus 15 being femtometers, FM. And this is going to be important for the remainder of this discussion of the strong nuclear force. So in this diagram, we can see two forces acting on a charged particle. So consider this blue circle to be a proton, and acting on it, we have both the strong nuclear force and the electrostatic force or electromagnetic force, same thing. Now we know that if you try to pull two protons together, they will repel due to the electrostatic force, which makes it very hard to consider a large number of protons in a nucleus being close together. So the strong force acts as a glue. It pulls it together and holds them in attraction, but only at an incredibly short range. So we consider the strong nuclear force only to act between 0.5 femtometers and 3 or 4, even 5 femtometers. It's an unclear maximum limit, but around that range. So I'm going to refer to it as 4. Now on the graph, which you will need to know, you can see that moving from furthest away, infinite range, there is a very weak electrostatic force impacting our particle, so our proton. And as that proton approaches another, it gradually increases in repulsion. And around about 4 femtometers, the strong force starts to kick in, and it gradually increases in its attraction until it overrides the electrostatic force. And at 0.5 femtometers, we see a peculiar thing happen, where suddenly this strong attractive force becomes totally repulsive. And this is the prevention of 2 protons or 2 particles in the nucleus overlapping, encountering each other in a contact. So this strong force is pulling in protons and neutrons at close range and binding them in a locked position, but preventing them colliding and overlapping. Now, radioactive decay is largely the same as when you covered it at GCSE, at least at this stage. Later on, we will go into greater depth with this. But for now, alpha decay is as you remember it, an alpha particle being 2 protons and 2 neutrons being released from a large nucleus, generally a proton-rich nucleus. And you can see the alpha particle, 2 protons, 2 neutrons. You need to be able to define it and also illustrate it in the equation as shown. As this is what's being removed, we're clearly removing 4 from our atomic mass and 2 from the atomic number. So this example, where uranium is decaying into thorium, this is essentially how it would look in the exam, where the alpha particle is missing, because it will be in the question, and you need to fill it in, along with the mass number and or the atomic number for thorium. Now, it's not about knowing what thorium is, it's about taking 4 from the top number and 2 from the bottom number, leaving us with thorium being 234 and 90. Beta decay is a little bit trickier. Again, it is a decay you covered at GCSE. A neutron-rich nucleus has a peculiar effect happen where a neutron in the nucleus turns into a proton. In doing so, it loses a tiny, tiny amount of mass, as illustrated by the bracketed values on your data booklet, and releases an electron. But it's not only an electron. At this level, we introduce an additional particle as part of this decay. So this symbol here represents an anti-neutrino. So the symbol itself is the neutrino, and the line above it, the hat, is the antiparticle aspect. Now, both of these will be detailed much more in a future session. But for now, you need to know it exists. So again, our example follows the same structure, missing values, missing beta particle, and in this case, the antineutrino. Now you're perfectly free to write down E for an electron instead of the beta symbol. Both are accepted, there would be no issue. The antineutrino must be added, and we know that the mass number has not changed. A neutron's turned to a proton, same mass. And the bottom number, the atomic number, is increased by 1 because of that additional proton. Now, gamma decay is largely irrelevant at this stage. Gamma is just the emission of extra energy, so there is no equation that you need to know. If gamma was to be included, it would just be an addition of a gamma symbol at the end of an alpha or beta decay. And that's it. Thank you for your time.